Now we're recording. No.
Thanks so much. Test file. You have to change it again for the function itself. Well, it would be temporary just to see if that single line of code will work. Because when you actually run the function later, you want to have data frame everywhere. You don't want to have frame variables space in the test file where it should be temporary experiment. Maybe just focus on the inside part. New test file, single bracket one. Just to get you in. Here's the error message. Okay. Library. Library Ggplot the end 2 at the end.
Okay, we're going to come back together as a group and work through this task now. So, okay, we're going to modify this function so it produces an XY scatter plot instead of a histogram for the 2 columns in the CSV file, and it does that if the mean value of the first column is negative. So to do this, I'm going to first copy this the function that we've already written and paste it below. I'm going to have to rewrite the whole thing, and then I'll just modify the parts that we think we should change. I'm going to start with the if condition instead of going first. So instead of having some condition on the names of the data frames columns, I want this to be a condition on the mean value of the first column in the data frame. So I'm going to remove this names of data frame bracket 1 is equal to blue and replace it with a different conditional statement that involves the mean of the first column.
It's not finding the data. What am I doing wrong?
Have you set the working directory to the folder with the data files? And when you try and read, like use read CSV, can you read the file in? Okay. Okay, so we're going to replace this names condition with something on the mean value. So I'm going to delete this names condition. So the idea here is that we would calculate the mean value of the first column and compare it to a number that helps tell us if that mean value is negative. So what number should we be comparing this mean value to? 0. Yeah, if it's less than 0, then it's a negative value. So we'll use that. We'll say mean. We want this to be the first column of the data frame. So again, I use the data frame, the temporary data frame name for where we'll be sending our file. So mean data frame, and I want to get the first column from the data frame. So how do I index a data frame to get the first column? Square brackets, and then what am I typing? 1 and a comma. Is that right? So I have, sure, yeah, space to give us the visual representation. Is this right? Right. So indexing 2-dimensional objects, first entry is the row, second entry is the column. So this will get me the first row and all of the columns. Do I want that, or do I want the first column and all of the rows? Right, first column and all the rows. So we need to move the 1 over to the other side of the comma. So if wherever the blank is, that's where we're getting all of those entries. So this gives me all of the rows with the blank here for the first, the 1 in the second spot. Okay, and then we're comparing this to be less than 0. So if this condition is true, mean of the data frame for the first column is less than 0, then we're going to make a plot. Okay. Before we go on to the next part, let's just see if that works. I'm going to change the name of this plotting function to be my plotting function 2, so I don't overwrite the previous function. And I'm going to just highlight everything here and press Command Return. So we'll still make a histogram if the condition's true, so we're just testing to see if we got the condition part to work, not the whole thing all at once. I still have this test file that's been read into R, so I'll just use my plotting function number 2 on the test file. So the data frame parameter I'll set equal to the name of our test file variable. And for the plot name, I'll just call it test again. We'll try running. Press Command Return, and I get an error message right off the bat. Yes. Error in this if statement, it says missing value where true false is needed. Okay, this is a good example where the error statement is not the most informative thing. It doesn't really, it just says we're missing a value where we should be having something that's true or false for doing the true or false condition for the if statement. So something about what happens in here that leads to not having a true or false value. So let's troubleshoot this statement first. Remember, we ran this code on our test file. So to troubleshoot, making a function, try testing code, we'll call them snippets, outside of the function. So for example, I'm going to try running mean value data frame for the first column less than 0, and I'll replace data frame, right? Because we haven't data frame, that's not a variable that actually exists. That's just the variable name that's going to be the placeholder inside of our function. The actual object I can test this on is the test file. So I'm going to replace data frame with test file outside of the function for this temporary test. And I'll run this line of code to see what happens. I get an NA. Right, when I just do this comparison, there's an NA that's returned. Which means maybe if I just highlight everything but the less than 0 side, so I just highlight the mean function execution and run that part of code, I get an NA. So that's where my NA is coming from. Which is to say, there's NAs in my data file that I didn't know about because I just assumed maybe it was good data and there's no NAs inside of it. So there's a few ways we can handle the NAs. We could open up the file itself, either within R or in the source, and try and remove the NAs before we even run the function. Or we could try and add something to this mean function that handles the NAs so we don't have to change the files themselves. Yeah, I like that one. It should work. It fixes this immediate problem. Maybe we have a problem later on. Again, which means, oh, maybe we should actually handle the NAs in the files themselves, but this is quick. We can do it right now. So we'll try it. Oh, good. I got a condition. I got a true or false returned as opposed to an NA. So we'll use that as the fix. I'll go back inside the function. I have if mean data frame for that first column, and then I'll add comma na.rm equals true. Highlight the function again. Execute it. Now try and run it on the test file to see what happens. Command return. Okay. No error. That's great. But no graph. Oh, that's unfortunate. Well, assuming that we got our mean condition working, and when we practice this on the actual test file we just ran it on, we were given a false, which means that this isn't going to make a graph. Or the mean value of the first column in the first data file is greater than 0. So no graph would be made for that test file. Okay, let's see if we can find a test file that'll actually make a graph. I'll try file number 2. Run the function, still no graph. Yeah, then it would work also. True. I'll try file number 3. Sorry, for folks online, the question was if we replace the condition to make it greater than 0 instead of less than 0, then the file should work. The function should work, and I said yes, it should totally work. Okay, we're trying on file 3. Oops. Try running the function. Okay, there we made a graph. We have a new graph as a histogram still. So this is a condition where we must have, it is true, the mean value of the first column is negative. So now we can start modifying inside the if statement in the function to produce an XY scatter plot instead of a histogram. So remember with histograms, in the aesthetics for the main Ggplot call, we only defined x equals the name of one column. This time I'm going to have an x equals and a y equals for making 2D graphs with Ggplot. But we have to be careful. We can't just use blue and black for the column names, because in some of these files, the column names change. As you saw earlier, some of them are green and yellow. So we want to use not the names of the columns, but indexing to access those columns. So we have something that's flexible since the names of the columns change from file to file. So here, we'll have x equals, we'll type again this temporary variable named data frame, and we'll use indexing to get the first column for x-axis. Space comma 1, and then outside the indexing I have a comma, and then y equals data frame square brackets space comma 2. So now it doesn't matter if the column names change from file to file. I'm always accessing the first and second column using indexing. Okay. We're not making a histogram, we're making a scatter plot, so I use the geom point function instead of geom histogram, and bins is not a parameter for scatter plots, so I'm getting rid of the bins altogether. And then finally, we'll keep this call for making a plot name, and I'll run this function. So now the function's been defined. We'll try it on our new example test file that should produce the scatter plot because it will pass that condition. And we have our scatter plot. Sorry, this is test file 3. Thanks. Okay, we're not going to move on to checking and changing the labels, but notice now since we've changed how we access the labels, accessing the columns by using indexing, that's the name that's been used for default for the access labels as opposed to the actual column names in this case. And so if we wanted to make this plot a little bit prettier, we'd have to add on more of those plot parameters to change access labels. But we'll leave those as data frame 1 and data frame 2 for now. Okay, any questions on writing this function? Yes. Yeah. So anytime we're indexing a two-dimensional object, we have to specify which row and which column we want. So we have a comma in there, the index for the row and the index for the column. And then the convention is always that the first entry is for the row and the second entry is for the column. And then if we leave either of those blank, then we're gonna, it'd be the same as listing the index for every value in that entry. It's just more convenient to just leave it blank. So by leaving it blank for the first entry for the row, but having a 1 in for the column, that means give me every single row in the first column. And if I'd made it a 2, in the second column. Any other questions, folks? Looks like the chat's blowing up. Okay, so the object data frame. So when you call the function, you will have data frame equals, and then you have in here like the name that you gave to the file that you read into R. Okay. And then this variable parameter named data frame that you have inside the function is the same everywhere you expect data frame to show up inside the function as well. There's no change in how you've typed the name. Notice when I highlight data frame, every instance of data frame inside the function is boxed to help you visually identify all the other instances of data frame. Is your mic on? I just unplugged it. It is now. Thanks. Okay, how about now for the microphone?
Yes.
Great, that's terrific. Okay. All right, well, that's fine, but okay. All right, I'm just trying to balance it.
I'm not getting the error anymore, but it's not trying the plot.
Are you, okay, did you read the third file into R? And there's no plot being generated.
I'm not getting an error, but I'm not getting the.
Okay, then what we'll do is new breakout session. For those of you where this is working, try to write a for loop that'll run through all the files in the directory using this function and print. It'll make a graph for each function. In this case, I'll give you a quick pointer. You'll need to put the when you call your plotting function inside of your loop, you'll have to put it inside of a print statement. So you'll have to have something like my plotting function inside of a print statement. I'll explain a little bit more about why that happens, but for now I'll just say that's what you'll have to do. And then the other hint I'll give you is that to access all the files in your working directory, you type dir with open close parentheses. So that'll help you kind of get moving your thread for loop. Okay, so for folks that this is working, go ahead and try and make that for loop. For folks where you're having other failures, I'll come around and try and help resolve the issue. So that's not funny. No, not the Hawks. Sorry. So I sent in either wherever you have the day 2 materials or the day 3 materials from emails, there should be that folder data files. Yeah, from that. You need the quotes on both sides. Didn't read it. Perfect. Okay. Here. So see the X here is telling you there's an error with this line of code. So now we have to parse all of the terms here and see what went wrong. We try highlighting just the mean, going from mean and then to the right, and see if that part runs. So yeah, now if we look at this part of the code, does this look correct for what we want it to be doing? So let's start. So we have mean of data frame, and then we're indexing. Do we want to index data frame, or we want to index the output from mean of data frame? See where you've got the start of the square brackets and the end of the parentheses. Yeah. No, sorry. You want the indexing brackets inside of the mean function at the end of the data frame.
Yeah. That should do it. Oh, perfect. There you go.
Which I have to do. I mean, I tried to forget.
Right. So this is in order to run the function, to execute it. We type its name like we type names for like other functions that we have. So the code that you have up above, that's the code where we're defining the function itself. Yeah. So if you run that, that's not actually going to do anything other than just make the function exist so that you can use it later.
Why do I have to do all of this? When I already have this defined.
Because like, so that'd be like if you just ran mean and you didn't put anything inside mean to calculate the mean of. Yeah, but those are just instructions. So those tell are what to do with the inputs into the function. They don't do anything for a specific object. They're meant to be used on any object that goes. Yeah, so that's where we specify all the parts. Yeah. So here, this X is telling you it looks like there's something in this line of code. And when you hover the mouse over the X, it gives you unexpected token, a right parentheses. Yeah. That one's got like little spell check sign on it. It might be. If you move the sure, yeah. No, that's constant. There is no plot. This is just, so all we've done is define the function. Yeah. No, so this is code that runs the function, and this is the code that builds the function.
Okay.
Yeah. Great. Ran, no errors. Ah, perfect. Because you still have to, inside the function, you're making a histogram. So you have to change in here this part for aesthetics. Instead of being X equals blue, you have to change that to there's an example there. Actually, I'll do it. So in the comment there, data frame brackets one. No, sorry. I mean, copy that part. Yeah. Just the X equals data. You already have the AES. Here, I'll just scroll up so you can see the example. Okay, it looks like we've got, we should have, so actually before I do this, just quick, raise your hand if you're able to get the scatter plots made. And if not, I can come around and help troubleshoot if you need help for there. Actually, sorry, other way around. Raise your hand real quick if you don't have the scatter plots to be made, and I can come help. Yeah, sure. so when you try to library Ggplot 2, it doesn't work. Let me try. Was this problem happening on V1 also? The Ggplot? Oh, yeah, yeah. I think, so. It's here. Oh, so okay, so if you do library Ggplot, this runs. I can do this. Should fix issue in the head. Oh, yeah. Okay. No, that's what just happened. When we click on it, it printed out the line, so it should be active. So maybe not try running the function again to see if it makes. I don't know. Let's come back. I don't think that part. That one. Yeah. Yep. Yeah. Perfect. Okay. We'll come back together now and start moving through this for loop. Real quick though, since this keeps coming up, I want to try and point this out together to folks. So these two blocks of code, the one here where we have my plotting function and then a bunch of code inside of my plotting function, is very different than the line below where we have the name my plotting function and then we've defined some of these terms inside. In the first case, we're literally writing the function itself. So we're giving it the instructions, we're giving it a name, telling it what it's going to do when we call it and run it. And then lower down here, this is where we're calling and running the function. Right? An analogy would be if we wrote a function for calculating the mean value of a vector, right? We would make a function, maybe call it my mean function. And it'd be some function that takes as its argument a vector. And then it would take that vector and it'd add everything together in the vector and divide it by the number of things in the vector, right? It would calculate the mean. So inside here would be code to calculate mean of numbers. Assuming you can spell calculate. And then when you want to use that function later, you would type my mean function. And then you would enter in some vector of numbers, 1 to 10, for example. The same way when you use the mean function, you just type mean for the name of the function, and then you insert inside of it a vector of numbers to run. So when I say things like go ahead and run the function again, execute the function, what I mean is we don't need to worry about rerunning and redefining the code that makes up the function itself because it's already been done. And now it exists in our global environment over here on the right. What we mean is instead just execute the function itself on a test data set or on an actual data set. And then in the future, we don't have to run both the function code and the function name itself together every time. We only need to define the function once, and then it's done. We can use it by simply calling its name once it's been defined. Yeah.
This time we always have to upload.
We always have to, yeah, same like when we use the mean function, we always have to provide it with a vector of numbers to calculate the mean of. Same thing here. we always have to provide our plotting function with some data frame. It could be test file, it could be test file number 2 if I've read into R a different test file and given it a different name. But yeah, if I don't put anything in here, when I want to run mean function, it's not going to do anything. You'll tell me error. Yeah, I have errors because there's nothing to execute. There's nothing to analyze.
Right, like file number 3, CSV, and then they will call it in the directory. They will like.
Nope. Yep. Unfortunately, R is not that intelligent. You have to be more explicit about these things because it doesn't know when I just type in quotes file _ 3.csv. R just thinks that I'm providing it with a character, a string. In quotes are the letters file _ 3.csv, and they mean absolutely nothing to R. Only when that shows up inside of a function like read.csv file equals that name, then it knows to look inside the working directory and find that file. Any other questions? Okay, let's try writing this loop that I encouraged you to make. So this is the part of the benefit of having this function. We can reuse this function over and over and over again in a loop. We have 20 data files we want to run. We want to make 20 graphs of them, but only for the ones that match our condition. So we're going to loop through everything in the directory and do it automatically, so we don't have to sit there and do each one by hand. So I mentioned you can use this dir function to access everything that's in your working directory. I type dir parentheses, and it gives me a return, a vector of file names in the working directory. So if I index dir, say with the number 1, and press command return, then it returns to me the file name for the first thing that shows up in the directory, alphanumerically ordered. So I can use that fact that I can index the working directory in this way to run through my loop and iterate which file I read into R one at a time. So I'm going to start up the loop, type it as for I in 1 : length of the directory. We talked about that yet. Sorry. We're introducing a new function, the length function. It tells you the length of a vector. So if I type length dir, I'm given the length of that vector. It's 20. There's 20 objects inside the directory. Alternatively, you could just type it in manually. It's called hard coding. You could type in the number 20 if you already know how many things are in the directory. That we're going to have 20 files we try to make graphs of. I'll leave this as length of directory. I have the example of this new function. Okay. There's loop for I in 1 to length of the directory. Okay, the first thing we have to do is we have to read into R the CSV file from the directory one at a time. And I'm going to give this a temporary name. I'll call it loop file, because this is the file that I'm reading in during my loop. Use the assignment operator and type read.csv. And now, instead of having to type the actual file name in quotes, I can index the working directory using my loop variable I, so that when the loop runs, the file name that we use inside of the read.csv function changes with each iteration of the loop. All of these files have headers, so I need to use the parameter header equals true. And then I should be able to then use loop file as the variable name that I put inside of my call to my plotting function. So the next part would be the call to my plotting function. I have to put that call to the function inside of a print command because it just so happens with R, if you try and generate loops automatically in a loop, they're not made unless they're put inside of a print statement. In the same way, when you're running a loop on doing operations on some kind of vector, it won't show you the result of the operations unless it's in a print statement. Except that instead of printing to the console now, we print to the graph window. Yeah.
So if you leave the directory blank inside parentheses, I'll just do the working directory.
Yes.
And if you wanted to put in another one.
That's an interesting question. Let's see. Yes, path equals, you could point to another working directory that way. Yeah. Sorry, focus on. The question was, if we leave the parentheses for directory blank, that automatically points to the working directory, and I said yes. And then the follow-up question was, so can we put inside the parentheses a path to another directory? And I said, great question. I don't think I've ever used it that way. And then we use tab completion down in the console on directory to find that, yes, you can specify the path, and we could point to another directory. Okay. Any other questions?
It is important that tab, like before loop and print, it's automatically like
Tab? Not an R. No. So yeah, this doesn't. The fact that it's automatically indenting is just being nice to us to make it visually clear what is inside the loop, what's not inside the loop. But yeah, if I deleted these things, it would still run. R doesn't read white space like Python does.
How important is like the placement of the brackets at the end, like in the bottom?
Sure. So a question about how important is it that the brackets here are placed at the end? Where exactly they're placed doesn't matter. The fact that they're there does matter. So if I deleted this, R doesn't know when my code for the for loop ends, and it'll just keep thinking the next thing that shows up is going to be inside the for loop until I finally get another bracket. But I could put this bracket at the end of the print statement, yeah, and we're okay. And I could even put everything, I could make it all be one line, I think. Or does that get us into trouble? Yeah, that gets us into trouble. So returns, yeah, returns are red. So I need at least one return for between the loop file and the print statement. Yeah, but I encourage you to use white space on the screen to help keep track of what begins and starts in different locations. It can be advantageous. Okay, so now inside the print statement, we type the name of our plotting function, my plotting function number 2. Inside of the plotting function for the data frame variable, I'm going to use this temporarily assigned loop file name. And then for the plot name, I'm going to use the index I, just so I have some way of keeping track of which plot we read in. Yeah, it's sufficient for now. Okay. I'm try running this code, highlight everything, and press Command Return. And we have 2 different outputs presented in the console. A bunch of nulls were returned, which is for all the instances where plots weren't generated, where that if condition wasn't met. And then on the right, we have our plots. So the last one that was made was 20. I can press this arrow key and go back, and file number 14 generated a plot, file number 13, file number 4, and finally we're back to the test file from before. Yeah.
Sorry, can you repeat the directory first?
Yeah, so directory, parentheses, square brackets, 1 would be the first file that shows up in the directory as ordered alphanumerically. Okay, any other questions?
The second, I noticed that it didn't make the criteria for the information.
Yeah, for the mean value.
So there was our if.
It's inside of the function. Right, so the function's already handling that for us.
So each node is for each CSV file. Each node is for each CSV file.
Each one that didn't have the first column average value less than 1. Yeah. Any other questions? Okay. We're almost an hour. Okay, so for the sake of time, so we can still get through looking at the remaining plots and just sort of demonstrating how you call different statistical methods in R. We're going to move forward to the next section, but there's one more activity that I had planned for working with this type of looping through directories and making graphs, where you print the graphs to file. So you save them as a file as opposed to putting them in R automatically. It's just adding in that last element we had from yesterday where we practiced saving graphs to file, only now you add that into the for loop. In the non-blank code, you have the code present for doing that, and I encourage you all to look at it because I think that that can be a helpful thing in the future. But for in-class time, we've got to move forward. So are there any other questions on functions, loops, if-else statements, all of this? We hit all this all at once. And this basically wraps up our time with it. Yes?
How would you write the loop function if the files that you're looking at don't start out long and don't necessarily?
So when you say they don't start,
Like,
oh.
if I were to dump the 25
Yes, files that aren't CSV files, for example. Okay, great. Great question. I can only give you half the answer because we don't have the time to go into it, but it gets into a great topic. So the question was, what if my files are in a directory that has more than just CSV files? So we can quickly simulate this. A bunch of CSVs, and I'll take these two TXT files, copy them, put them in here, those data files. So now I've got a working directory that has, where's our, here we go. I have, yes, CSV files and TXT files. And if I try and run this loop again, let's see what happens. I have errors because R doesn't like trying to read TXT files as CSVs. We have to do something different. So in this instance, you try to subset your directory so that you're only working with the subset of the directory that has the right file name, the right CSVs. So I want some way to scan through every item in this vector of file names and grab just the ones that have .csv in the file name and ignore everything else. And interestingly, in R, so Python has some nice ways to do that automatically, where you can sort of search for strings, for entries in strings. R doesn't. You have to use a whole separate set of functions. You search for the phrase regular expressions, or I think the function is regex, not reg. I only have to do this occasionally, so I tend to forget. There, yeah, regexec. I think that's the one you want. Anyways, the idea is it's a function where you provide to the function a string, and then you tell it what pattern to look for in the string. So we put in here, I think the pattern would be look for .csvs, and then the text. Yeah, so here's the character vector where matches are sought. So text, this would be directory square brackets I. So you put that random thing in there, and then you have it search for the CSV, and then this either returns, I think, true or false if it's there, or maybe gives you indices. There's a few different ways you can try and run this type of thing, but this is essentially how you would perform that type of operation. I can't, I'm afraid to run this line right here because I'm not, well, let's see. I'll just, oh, great, a true. That doesn't make sense though, because dir1 should be a txt file. Yeah, this is what happens trying to do that on the fly. Regular expressions, there's lots of information online. It's a very, it's a technique used for lots of types of analyses, and in this case, it's just a handy tool to index our directory. I think the other one, grep, that's the function that I actually remember in this case, but for grab replace, usually use them in combination. Okay, any other questions? Okay, so jumping forward, going to look, so we're gonna basically burn through a bunch of different types of graphs real fast. This is more just sort of a survey of graphs that exist and how you can call them quickly with Ggplot, and some aspects of, yeah, and just start making graphs. And then we'll do a similar type of exercise with a variety of statistical functions that exist in R. So density plots, box plots, and violin plots. We're going to be looking at the Hawks data again for this activity, so we need to change our working directory to wherever the Hawks are. Let's see, I'm going to use this fashion choose directory. Let's see, I don't want the data files anymore. I want my parent day 3 directory, which is where I have all of my day 3 material, including the Hawks day 3 CSV file. So this is what I have for my set working directory call. And I need to read into R the Hawks data file. So I assign it the name Hawks, and I'll use the read.table function. File equals, I'm going to tab complete to get me to the Hawks day 3 CSV, comma, header is true. There are column names. It is a comma separated file. So I need sep equals in quotes with a comma. And then finally, I keep planting NAs in all of our data files to mess with us. So we should probably assume that there are NAs in this one as well. So I'll use the na.strings argument to specify the potential for either blank entries or NA capital N, capital A instances to make sure we get everything converted to NAs. Then I'll press Command Return. And then finally, if we remember, this Hawks data frame does have a bunch of NAs for the sex of the Hawks. So I'm going to remove those again using the NA omit function, and then assign that new data frame to the variable name Hawks.trim, for being a trimmed version of the Hawks data frame. So Hawks.trim is assigned as na.omit the Hawks data frame. Remember, the na omit function removes every row that has an NA in any of the columns of that row. Press Command Return. Now I have the trimmed Hawks data frame with only 327 rows and 6 variables. So let's make some new plots. Just so that we can have a refresher of what, these are all 1D plots. The first 1D plot we made was histograms. So I'll real quick generate a histogram so we can compare all these different ones to histograms. So here data is, I have Ggplot, data is Hawks.trim. For the aesthetics, the x-axis will be the tail column in the Hawks data file. And I'm going to fill by species again. And a plus sign. And then here I'm just going to have the geom histogram function call, and I'm going to specify 20 bins. I'll run those 2 lines of code, highlight, Command Return, and we should have our histogram as we had before. We didn't add any parameters, so we have the histogram bins are stacked on top of each other, and they have no transparency. But that's fine. I just wanted to be able to see again, oh yes, this is what they look like with histograms, where we have the absolute counts on the vertical axis. So maybe we're interested in having these not be made as histograms. We want to have smooth density plots made. To do that, we have, I'm going to highlight this ggplot geom histogram function call I used before, paste it below, and all I have to do is remove the geom histogram function and replace it with geom density. Open close parentheses. And then this will make a density plot of the histogram, well, a density plot of our data. So highlight these two lines, press Command Return, and we now have density plots for that data. Real quick, since these are not overlapping, I'm going to use the alpha parameter inside of geom density to make these transparent. So I'll set alpha equals 0.5 inside of the geom density function call and rerun these two lines. And now I can see in full all three of these density plots. An important thing for those of you who aren't familiar with sort of the subtle differences between these different types of graphs, if maybe these are new, is that the way density plots are made is that they've been basically all standardized in terms of their heights. Whereas with the histograms, you have absolute counts of values. So notice, right, the red-tailed hawks, we only have 4 data points for the red-tailed hawks. And in the box, or in the histogram, it's very clear that we only have 4 data points there because this is an absolute count of the number of instances values occur. Whereas the density plots, because of how they're calculated and normalized, it would appear that we have more red-tailed data than we actually do in this representation of the data. So this is sort of a trade-off between whether you're using histograms or density plots due to the nature of how density plots are built. Yes. The 0.5, so that's for the transparency. So that's to make they're 50% transparent, so we can kind of see through the different layers of the density plots.
That looks great.
Yeah, Ggplot for the win, right? So we literally did all the basic, and they're very nice looking. Aside from the fact they misrepresent the red tail data. It's bad. Oh, yes. For those of you, right, we're at this problem. Names of hawks.trim, close parentheses, square bracket 1, because the species is the name of the first column, and then assignment operator, less than sign, hyphen sign, in quotes, capital S, lowercase p, ECIES. And that should do it. Okay. All right, so maybe you don't use these kinds of graphs. Maybe you instead use box plots for your data or bar plots. Again, to make those from one-dimensional categorical data, it's a very straightforward change from what we have so far. Just instead of geom density, I'm going to replace it with geom box plot. And I'll remove the alpha parameter because the box plots are automatically non-overlapping. So highlight these two lines, press Command or Control Return, row, oh, yes. Yes, of course. Okay, box plots. Let's remember, box plots, we're gonna have our axes change for box plots. As we move along the horizontal axis, that's typically where we have our if we have vertical box plots or vertical bar plots. As we move along the horizontal axis, that's our categorical variable, so that'll be our 3 different species. And then the vertical axis is going to be the actual values for the continuous variable tail. So I need to change what I have inside of aesthetics. For the now that I'm making a box plot, I need to make x equal species, and instead of fill, I have y equals tail. Try highlighting these 2 lines, press Command Return. Great, and now we have 3 box plots. or box and whisker plots, if you like. And you could switch the X and the Y, and then you just have horizontal box plots. There's nothing inherently different there. It's just been rotated. So as an example, X and Y aesthetics, that should have worked. It usually works. That's interesting. It didn't actually make the box.
Have the color.
Yeah, that's interesting. It didn't have that problem before with vertical. Let me try coming back. Anyways, if we want to fill for color, we still can. We can use the fill parameter and fill by the species so that these, they become colored box and whisker plots. Yeah.
Is the middle line the median?
I always forget this because I never use these. So I think, yeah, the middle line's median, and then the outer parts of the box are like the quartiles. Yeah, and then the bars have something to do with, I think, the quartiles and the next quartiles and the outliers. Yeah, perfect, thank you. And then, yeah, so like these dots here are like extreme outliers too. Cool, great. Okay.
The gray, like the background.
Yes, I don't remember exactly how. Yeah, you totally can. Yeah, and it's I've done it for other graphs. You can just like Google Ggplot remove gray background, and you'll have like 50 responses, I'm sure. Any more questions? This is great. You like graphs? Okay. Well, so real quick, trying to motivate the next graph. So we can see with the nature of these box plots, these aren't symmetric data sets. As we saw with our histograms and our, where are they? Yeah, the histograms, they're definitely not very symmetric. Many of them are bimodal. So maybe you don't want the box plot to represent the graph. You'd like a violin plot so you can see some of that structure. We can make a violin plot. So, right, similar to a box plot in presentation, it's just that instead of making it as a box, we have the density plots, really is what they are. They're rotated and stretched. So we'll take the box plot command from above, copy and paste it below, and replace box plot here with violin. And then press, highlight the two lines, press Command or Control Return, and we should now have violin plots for the data. And as I mentioned, these really are, they're the density plots from before. They've just been rotated so they're vertical instead of horizontal, and then they've been mirrored over a vertical axis, so they look nice, like violins. As
Secrets to updating the plot, one person's saying that stuff.
If you're having problems viewing new graphs, maybe, yeah, there's some kind of hang up and you can't make a new graph. Yeah, I just clear all the graphs that I have and then just start new. Because that should terminate if it's trying to generate more new graphs. Okay. Okay, with the violin plots, there's another parameter you can add that modifies how the tails are presented. So I'll add here another call where inside GM violin, we add the parameter trim equals false. You'll notice for some of these, some of the tails in these graphs, they've been cut off. So if you want to include everything, you have the parameter trim equals false. We rerun it, and then now we have the full distributions, the full density plots presented. For some reason, it's just how it's ordering the categories. They also look like they're flipped upside down, and you maybe have different data. This is the Hawks data for day 3. And looking at the tail variable. I mean, you're generating the graphs. That's not the problem. It just looks like you're maybe using different data. Cool. Okay, great. But maybe you still like the information presented from the box plot in terms of having that quartile information, but you also like the presentation of the information of the violin plot. Wouldn't it be great if you could do both at the same time? Yes, you can. So to do that, we'll make our violin plot with trim equals false. And at the end of the call to make geom violin, I have a plus, and I'm going to follow this up with geom box plot. And then I can highlight all three of these lines, press Command or Control Return. What did you say? Oh, okay, error, don't know how to add geom box plot to a plot. Okay, that's not the most helpful error. If I just look at how I wrote geom box plot, I realize I forgot to include the parentheses at the end of that function. So now try again, highlight these three lines, press Command or Control Return, and great, now I have actually a rather hideous graph. I have these box plots that are obscuring my violin plots. It's kind of backfired, but we can change that. The box plot function has a parameter called width that allows you to vary the width of the box plots so that we can make them more narrow and hopefully still see the important part of the violin plots. So I'll type inside the function width equals 0.2. Highlight these three lines, press Command or Control Return, and now I have violin plots with the box plots made internal to them. So we have both the multimodal structure of the distributions made clear with the violin plots, and then we also have the statistical information from the quartile presentation and the box plots overlaid. Don't forget about histograms. Oh, we did that. We started with histograms.
Sorry, when you say trim equal to false, what do you say R? What do you want from R?
Like, what is this doing? So see how these tails for these distributions are they come down to a point. If I remove the trim equals false command entirely, let's do it from this one, and run this code. So trim equals, so we specified trim equals false, which means that R assumes trim equals true all the time. A lot of these parameters have default settings, so that unless you say otherwise, it runs one way. And so since I removed it, well, what that means is that R assumes trim equals true every time I want to run this graph, and then it cuts off the ends of the violin plots, as long as they're not going down. And so if you make it false, then it keeps that information in the graph. It does not trim the violin plots. Yep. Okay. Any more questions about these three 1D graph options? Yes, sure.
I'm getting another same question.
Let me see if I have that problem.
Clear that and then nothing replots.
I have a guess about what's happening. Clearing the plot, I try and make all the plots, or a single plot. You cleared it by pressing the broom?
Yeah.
Clear all plots. Hit yes. Highlight, execute, Ggplot. You could try loading Ggplot as a library again. That might have something to do with that.
Tried that, no luck. So it's just a graphics issue.
What?
I'll talk about restart our studio.
Yeah, I was gonna say the next thing is you might just need to restart our studio. That's
just graphics error.
interesting. Yeah. Don't forget to save. And then restart. Okay, any other questions? Yes. Yes, all of that is a part of day one. And so there's examples there from the code that was shared. So it all works the same. You just keep adding, we add the command to change title, X label, Y label for doing that, or we add the command for the theme to change the font style. So it's possible. I'm just stopping short of that with these for time. And the same with the legend. You'll notice now that we have two graphics, violins and the box plots, our legends have a fill for the violins, and then there's tiny little on top. So with the legend parameters we work with, you could also modify that. Yeah, it's kind of neat, but also kind of weird. Like that's a tiny box plot in the legend. Yes. I'm sure we can. Off the top of my head, I don't know how. But anytime, great question, great idea, sounds cool. Let's see, Ggplot. In Google, we're searching Ggplot, show points with violin plot. If I just type show points, like I might just get an XY scatter plot. So I'm going to try and add in here. I want to do this on top of a violin plot. Let's see what we get. So I don't see anything about points here. Some stuff about violin plots, box plots. I want something that shows me plotting points with how to show whiskers and points. Whiskers and points on violin plots. That's what I want. How to show whiskers and points on violin plots. Someone has some data they show on Stack Overflow. They tried making this graph. It's not doing what they want. Here's their questions. Here's some quick responses. An answer with the green check mark. May I suggest using some other packages and plotting methods instead? Okay, that's not an uncommon response. But they nicely provided a bunch of code to help them do it, and then there they have their graphs. So it might not be easy with Ggplot. There might be another response. Maybe if I searched show points with box plot instead of violin plot, I'd have had a better response. Or maybe now it's time to try using different plotting options in R. This type of exercise is why I bounce back and forth between Ggplot and Plot Basic, because I have an idea of the graph I want to make, and if whatever is easier to do it in, that's what I just find the code online from.
Somebody wants to know if there's a volcano plot. I've never heard of it.
There is a volcano plot. Yes, tab complete found something when I typed volcano, but there's not much more going on. I can try help parentheses volcano. Yes, definitely there. Topographic information on Auckland's. Oh, that's a data set, the volcano data set. Ironic. Yes, volcano plots exist in R. I wasn't going to make them as part of this exercise, but I'm going to point to some resources at the end of the day where I'm sure there's volcano plot code there. Okay. Sorry, any other question? This is great. Okay. All right. Let's where we're yeah, we'll burn through the 1D stats functions and then we can break. So finally, you might ask, what about all those statistical tests? As we mentioned at the very beginning, we said that R was originally designed for doing statistics. It has many statistical tests encoded, although interestingly, I tried searching for permutation tests to see if it had that, and it's not automatic. You have to, not as, if you type permute, tab complete doesn't have anything. But it does have for Bootstrap, so it might just be people assume you can figure it out. But Bootstrap, they wrote their own code. Sorry, this is in reference to the other R workshop on modern statistical methods. So I guess that maybe is to say some of the modern methods aren't pre-encoded in R, but a lot of the non-modern t-test is. Yeah, parametric, thank you. That's good. Okay, so we're going to highlight a few, just real quick show you how you call them as functions, how you access the information inside them. I do have to say the caveat, I will not be discussing the validity of using these tests on these data. This is merely just to say, here's where they exist. So first, t-tests on tail lengths for the sharp-shinned Cooper's hawk species. So there's a caution again. I'm going to keep saying this caution because one's back. So maybe you want to run a t-test to compare. Great thing with a lot of these things in R, the name of the function is very close to the name of the thing you thought it would be. That test goes up complete when I do t dot t. It's the only thing in R with that name. Test. So inside we can define. It's not giving us a full explanation, but we can run two-sided, two-sided, one-sided tests. It just depends on whether or not we give our one distribution or two distributions, and then how we specify separate parameters later on. I'm going to give it two distributions because we'll just demonstrate real quick a two-sample test, and we'll do the Hawks data for the tail measurements. And then I want to compare tail measurements for one species versus tail measurements for another species. So I'm going to index this vector of tail data with a which function. And inside the which function, I'm going to use the Hawks $species column double equal sign for SS with the sharp-shinned hawks. So we're indexing by grabbing all of the species names that equal sharp-shinned, and then using those indices to then grab the tail values that correspond to those. And then we're going to compare that to the distribution for Cooper's hawks. So I have comma at the end of this. Now that I've defined the first vector, tab complete for t-test shows me other parameters I can specify. So Y is for having the second distribution, which is what I'm going to provide for the other birds. So I replace SS with CH. And then if I wanted, I can specify other parameters and find them with tab completion. So, so for alternative, we can specify if we're doing two-sided, greater or less than for one-sided tests. If they're one-sided tests, we can specify the true value of the mean that we want to test against. We can specify if it's paired data or not paired data. Assumptions about the variance or confidence level that we want to look at. I'm not going to specify that much. It's just say, here's how we can run the test flat out. Press command return on this function call to the test, and R runs the test, no questions asked. And it produces all kinds of information about the results of the test. R's determination based off of these results about whether or not you should be, what do we say here, the alternative hypothesis or rejecting null hypotheses, information about the confidence interval you didn't specify, so it assumes the default 95% confidence interval specification, and it's done. So coming back to the caution, this is what's the t-test we needed to be normalized data, and we saw that these were bimodal data sets because we have both sexes of birds, male and female, for each one, so we have two peaks for each distribution. R doesn't care, R runs the test. So, it's really important. R is not going to check assumptions for you. That's something that you have to do yourself. R is a tool, and it will run no matter what. Anyways, assuming this was the right test to run, maybe you want to access this information from the test. We can do that if we assign the function call for this test to a variable name. So I'm going to make a variable name. I'll call it t_test_results. Use the assignment operator, and then I'm going to copy and paste this call to the t-test above and assign that to the variable name t-test results. So now when I run this line of code, highlight both sections, press command return. Now the results weren't printed to the console. They've instead been assigned to a variable name. And if I go into my global environment, I can find here under the data section something called t-test results. It's a list object with 9 entries. If I press on the little arrow sign, it shows me some of the summary information about each of those objects. Or alternatively, I can just type the name of the variable in the console, t_test_results. Press return. Okay, I get the same output that I did before, but if we try instead, it's interesting, access t-test results with a $, index operation. Each of the entries in the list were given a name, so I can access them by the name of that entry in the list. So with the $, I can have tab completion kick in, and now I can find, oh, if I want to get the statistic value, it's $statistic. If I want to get, yeah, I do p-value. Here's p-value. If I want to access confidence intervals, other statements, other outputs from the test, they're all provided there. Yes?
I'm getting an error. It says in the t-test, it says not enough x observations. Do you think?
Oh, interesting. That might have to do with how you're indexing the data and you're actually only providing like empty vectors.
In this test, R doesn't pay attention to NA because I think the marks.
You left the NAs in there. Yeah, and the same with the plotting. A lot of the plotting doesn't care with it, but it handles NAs automatically. It's not a problem. And so it knows how to treat those.
And also, is there any test in R that check the
Not automatically. I mean, you can make QQ plots, and I think that
other because there are some tests in other, like for example, SATA, we can check the normality with p-value. So, for example, the hypothesis is this data normal?
right.
And then it's the null hypothesis, and then it will give us the p-value, and by this p-value we can understand that.
If it's sure. Not with just t-test. There's I think QQ plot for making a quartile. Is that right? A quartile plot. This is the other reason I'm not trying to.
I do that for the normality, we can check it in Histogram, which is one way. And then if
You mean just make a histogram of the data? Sure.
It says that's normal. But other than this, there are some tests that if
Yeah. So again, I don't know off the top of my head, just a test that says, is this a normal distribution? You might have to actually make something a little more rigorous out of it, but I think QQ plots are a way of doing that.
He's asking the test if the distribution is normal.
Yeah.
Shapiro-Wilks.
does it exist in R?
Almost certainly.
Okay. Should we do other program?
Yes, Shapiro.test is, I typed SHA. Yeah, so yeah, if you know the name of the test, there's a really good chance it exists in R, and you can just type. So this is when I was joking about looking for permutation versus bootstrapping. I know bootstrapping exists because I've used it in R, and if I can type boot, then I get a whole library for bootstrapping. That's the boot : means that there's a library. But with permutation, I get nothing. I get % for, I don't know what that is, but nothing about. So yeah, so if you know the name of the test for what you wanted to do, just try starting to type the name of the test, and there's a really good chance that it's there. Yeah. That interesting. I can't immediately tell you what's different. Interesting. Can we view it like it's a script or a table? I don't know. View t-test results. Yes, you can do that. I can read the names if that might go faster too. You have to, cool. I don't. I cannot say why. That might have something to do about versioning of R in total for what we have. You're on a Mac, so it's definitely not that. Yeah. Okay. KS test. That one also exists. Going just to the next test. So maybe you want to compare not just means for distributions, but also whole distributions themselves. KS, Kolmogorov-Smirnov. Some folks use it, some folks don't. But it's a test for comparing two distributions, so I can just copy paste these x equals 1 value, y equals another vector, and again, I can run the test. I get a caution about the fact that I have tied values between the two data sets, but otherwise it runs and it gives me output. And then ANOVAs are also here as well. Let's see. Yeah, that's fine. So to do the Anova example for us real quick, we have to load another package because the data set we're using happens to have, let's get this right, it's not balanced. We have different numbers of observations for the different categorical variables. So we need an extra package that can handle that type of data for an Anova test. So we'll load this real quick using the install packages function. We use the car package, CAR. I'll press command return to load that package or install the package. For me, I've already installed it, so I get this warning saying, oh, if you want to update it, we're going to restart R. And I say, sure, that's fine. That shouldn't be a big deal. And then now that the package is currently installing or updating, now I can load it with the library call for the car package. Okay. All right, so for this example of the Anova test, the idea is that we're going to compare, we're going to examine how the categorical variables of, what do I use, age and sex influence the tail measurements for just one species of the birds, the sharp-shinned hawks. So we're going to subset our data so that we're only working with the sharp-shinned hawks. I'm going to assign a new variable ss.hawks, and I have working from the hawks trim data set. That's the one I'm going to index. And I want to grab all of the species of hawks that are sharp-shinned. So I'm using the which function. Inside the which function, I type hawks $species double equals, and then in quotes SS. So that now we are identifying all of the rows of species who have SS as their entry, and those are the rows we will use to subset this data frame by. I want all of the columns though, so I'm going to have a comma and then a space. So I make sure I copy over all of the columns of that data set. So now I have a subset of the hawks data set that is just the sharp-shinned hawks. Oh, we should check though, I made something that could be very bad. I indexed the hawks.trim data frame, but in my which function I use the other file hawks, which means I'm going to have mismatching rows from one in data frame for the rows of another. So I don't want to do that. I need to use hawks.trim for both. I apologize. And then press command return and run that line. Okay. So now for this Anova, again, this is this use happens to be particular for this case where we have unbalanced data. So first we'll define an object where we're going to send, we'll define it, it's called an Anova object here. So we have my Anova is assigned, and then we have AOV for the Anova function. And then we have to specify a formula for how the comparison that we're doing. And this formula is, we're interested in looking at tail measurements and how those tail measurements vary as a result of different categorical variables. So we start with the tail variable, and then we use the tilde sign, which is in this case, it's the equation operator for how does this first variable vary as a function of these other variables. You have to use the tilde sign for that. Then on the other side, I have the column names age, and then the multiplication operator with the column name for sex. And so that's how we would input to R, that this is the relationship we want to explore, how the continuous variable tail varies as a function of the categorical variables age and sex. Finally, we specify the data set that this comes from so that R knows to look inside of that data set for those column names, tail, age, sex. And then we can run that line of code. And then for this example, it's a two-step process, unfortunately, so we have to run another instance of an Anova function. This one is capital A, lowercase nova. And then we provide it with this my Anova variable we defined previously, and then we specify the type. And here is where we get to clarify that this was a test for an unbalanced study. The type equals 3 is the condition pertaining to our scenario. If you have balanced data, I think you can skip this second line and you can just run the first line and it's sufficient. Okay, so highlight these two lines, press Command Return, and now we get as output from this the output of our Anova test. So we have, as I understand, this PR greater than F column corresponds to your p-value column, and it's indicating which of your variables. So here's our age variable, and our sex variable indicates which of these actually had an influence or didn't have an influence on variation in your tail measurements. Yes?
This is automatically one-way.
I
One-way ANOVA, depending on two groups and two conditions. Then to be two-way ANOVA, this is like one-way ANOVA.
I don't know. I don't do ANOVAs. Do you have an answer to this?
What was the question?
Is it if this is automatically a one-way ANOVA or not? Since we have two variables.
I don't know.
Maybe in our results we have age, sex, and then age colon sex, which I understand is to be the condition of the two variables
Looks like a two-way.
together.
with the intersection.
Yeah, is that getting to your question?
That looks like two-way, but it's not specified.
We have to look more into the documentation for it. So yeah, so at that point I'd say, if this is something you want to run and you have more questions about how it works, I suggest first to help AOV and see what shows up down here for what kind of assumptions or how it's operating and running.
So I don't know if anyone else had this problem, but the install car I think worked, but when you load it, it tries. Did anyone else get a package called data.table?
Yeah.
Error.
Yeah.
Like it's loading. Do you mean to load car data? Because it looks like library car is trying to load car data. When I installed the package, it failed to install the table. So maybe it's different.
Interesting.
Like install packages said,
There is no package called data table.
yeah, data.table.
In which case, okay, so it told you the name of the package that you need to install that you don't have.
I did it and it went through and installed, but it exited with non-zero status for that.
Oh, for installing the next package.
And I click yes.
So what's the name of this package?
Same one you did. Install quote car.
No, for the next one. It said you didn't have another package.
Data.table.
Data.table. So if you have these cases where you try to install a package and you were told you don't have this other package and it terminates, I thought it used to prompt you to say, would you like to install this other one? So what I end up doing is I just manually install that package if it says I don't have it. Or you can use a parameter inside your first function call, install package, which is dependencies, which should say, yeah, indicating whether to also install uninstalled packages on which the one you first asked depends on.
We clicked yes, it installed all the dependencies. It just failed.
Just oh, in that case, I don't know if I have a good answer.
That's a good idea.
Let me say, do you want to install from sources the package with
Yes.
this compilation?
Yeah.
And then doesn't,
Yeah, data table had non-zero exit status. We got a couple people online with it.
I had that too. So I have this problem as well, apparently, and somehow I'm able to actually run this. So
You're calling library car in quotes.
I did the second time to see if that made a difference. But the problem is it doesn't produce the usual, well, yeah, no matter what, quotes or no quotes, I don't get.
Oh
anything other than just a caret return. Have you folks who had this exit status problem with this package, did you try running these 2 lines for the Anova anyways? It didn't work. The capital one, right? That's the one that's supposed to come with this other package. Cool.
You said if you do it binary, it works.
Yeah, when you say type equals binary, for the data table, that works.
Type equals, in quotes, binary?
Yeah.
That worked.
Hey,
Thank you so
very
much.
Nice.
It's Stack Overflow.
Terrific. We have a new line of code to try running. Hopefully fix this problem. It worked, perfect. Okay, so for folks, so if you're having trouble with installing this data.table package is needed for the car package, try install.packages, in quotes, data.table, and then add on the parameter type equals binary, and that should help resolve this issue. Oh, the problems we run into. Okay, we're gonna pause there, take a break, and then we'll come back and go through a couple examples for 2D methods, a combination of some other plots and basic stats tests that are commonly requested. Yes? Huh? Oh, sure, yeah. So let's break for 5 minutes. Come back. Oh, yeah, we'll use this clock. Come back at 11:20 per computer clocks.
It's data.table. Sorry, a period.
No, I don't have a sign. Let me go get that. Good question.
Yeah, I was gonna just do it at the end. But
People leave. I'll do it.
yeah, it's it's. Sorry.
Here you go. Thank you much.
So it turns out those of you guys been doing a lot of late errands, workshops, the ones that show up physically. Turns out there is a way to use the applications that you don't set up 72 hours of the workshop and adding. So I explained why there's a lot of. I'll keep that in mind.
There's nothing about me. I like having people, but no.
No,
So to just more learning.
they go there online.
Great. Sure. Yeah. Next try library. So go back up for the car. No, not close.
This is a channel. Yeah. So this is why it's popping 55 pages.
Now it's different. Now it says my Anova Example.
I'm wondering if he's getting messages.
So inside, you're calling this function, and inside you're using the variable name.
I think they just are messages.
Yeah. Yeah, I think that's the same. I might have just general chat. Yeah.
My Anova like that, which means my Anova doesn't exist in here. Right. 211. Yeah. Perfect. There it is. Yeah, if you just try and run the no, it ran. Here's the console output for what you ran. Here's the output of the test, and then just a warning that you have contextual data. Thought we could do just two. So again, if you run it and then see what the output looks like, the output. So it tells how the response curve of tail is conditional on age, sex, and the interaction of those two. Just turn those age column sex. So how is tail different within the age group? Because the age group has two categories. Yeah, right. So remember, so age has the adults and the infants, and then sex has male and female. It's the interaction terminology. So multiplication with sex, and then try running it. Looks like it does. And it might just default back to the t-test for that. Yeah. Then that will do a t-test. I don't know what those are, but you could, so you could try searching. Yeah. The amount of searches that you need, or the amount of searches you have to get a certain power. Yeah. I've never done study in that direction. So there might be a built-in function for doing that, or there might just be, again, like Google, and someone just said, here's how you do it for this test. There should be, yeah, either in R or online, someone close to us has pretty straightforward. Yeah.
Okay, let's start back up again. Okay, so we'll move on to now looking at some two-dimensional options.
As we get started again.
Oh, thank you.
Sign in to the fact sheet.
Let's see. we are going to run out of time. Let's do that. Okay.
You don't have to get through everything.
No, I've already cut out stuff. When I found out that I only had 2.5 hours. Anyways, okay. So linear regressions, pretty common object to be able to do in R. So suppose you want to fit a linear model on the tail versus wing relationship for the sharp-finned hawks. This is again a very convenient function. It's just LM for linear model. We're going to treat this the same way we did with the previous tests, where I'm going to assign the output of this test to a variable name so we can access the information separately. So I'm going to use SS for sharp-shinned, .tw for tail wing, .lm for linear model. Again, it's just a variable name. You're free to write your own name if you find one you think is more convenient. The important part is what comes next. We have LM for linear model for the name of the linear model function. And then inside, again, now we're going to specify first the formula, the variables relationship that we want to examine. And I said tail versus wing. So I have tail, tilde, wing, comma, and then I need to specify the data set from which these variable names come from or correspond to, and that's the ss.hawks data set. I press command return. We have no output because again we saved the output to the variable name sstw.lm, and it shows up in our data in our environment similarly as the Anova results did or the t-test results did as this list with a bunch of objects inside. If I type summary and then enter into summary the name of this linear model output, then I have printed to the console summary information for the results of that test. And it reminds you, okay, what was it that you actually asked us to do for this linear model? And then we have residual information, coefficient values, and then information for R-squared values, statistical values, standard errors. Same message as before. Whether or not there should be a linear relationship in your data, R will run the code. So again, it's not checking assumptions for you. It's just doing what you asked it to do, which is do the test, run the model, and calculate all of the statistical measures at the end. With Ggplot, we can really quickly add a linear regression to our data. So we'll bring back up our Ggplot function commands for making an XY scatter plot of data. So Ggplot data equals ss.hawks. And for our aesthetics, we're going to have x equals wing to put wing on the x-axis, and y equals tail to put tail on the vertical axis. Close parentheses, plus sign, because now I'm going to add the geom point function to make the scatter plot out of the data. And then I'm going to add on top of that, I want to have something that makes the linear model graph. So I hit return, sorry, plus sign return. And now for adding a linear model with a graph, I type stat_smooth for stat smooth. It's an object from the statistical library, and it's a smooth object because it's a continuous curve that's being plotted. And then inside, I type method equals, in quotes, LM for the type of statistical interpolation that I want to be making and graphing. Highlight these lines of code, press command return. Uh-oh, could not find Ggplot. That might have to do with the fact that I restarted my session. No big deal. Just add a function call to load the Ggplot library. Then try running these lines of code again. Great.
You set your R to load all your libraries that you want at the beginning.
Mm-hmm. Yeah, but the problem was that I restarted the session because I had this problem with the packages. No. No, because if you restart the session, then, I mean, I would just have to scroll back to the top and run the code for the libraries. It's not going to automatically well, I don't know, I guess maybe somewhere in the preferences for RStudio, you could set some parameters to automatically load a certain number of packages on every time you start and load RStudio. I usually just put them at the top of a script file. I've never tried to see if I can load them with the software. Okay, so we run those 3 lines of code, and here we have our graph from before, our scatter plot. Again, this is just for the Sharpshin data, so we only have 1 pair of clusters. And again, these clusters are based on the sex of the birds, tail versus wing. And then that last function called the stat method lm plotted the line that corresponds to the results from a linear regression model on that data. Ggplot tends to add confidence bounds on these graphs. So you'll notice this darker gray sort of envelope around the blue line. That's what that corresponds to. You can toggle that to turn it off. I'm blanking on which parameter you might use for it. But I know it's possible because I've done it before. Oh yeah, here, SE, display confidence interval around smooth. I think that default is true. If I set it to false, then I get a graph. Yep, there we go. I get a graph that doesn't have those confidence intervals around the curve. Okay. That's the example for linear models for the shortest possible intro to how to run them and how to graph them. Are there questions from folks? Yes.
I had a warning message that you made 181 rows containing non-finite values for stats.
Ooh, it sounds like you might have used not the SSHawks data, and that maybe there's NAs in the data, and so it pulled those out.
I see.
Okay. What did I have for breakout? Make a violin and a scatter plot. I'm going to add fitted lines. Use 1, 2 of those. Yeah, that's good. Perfect. Oh, my pages. There, okay, cluster graphs. This one's quick. Okay, so you may be interested in automated methods for identifying clusters in your data. This kind of gets us into a little bit of the realm of machine learning, but only lightly. We're going to real quick talk about a function for doing just that, automatically identifying clusters that exist in your data. This is called k-means clustering. The way it works is that the algorithm sort of either you provide it with test values or it guesses locations in your data where centers of clusters might exist. And then based on the number of clusters you tell it to look for, so here we could provide it with this data set. We see these 2 clusters, we could say, okay, look, code, there's 2 clusters there I want you to find. And maybe we tell it some candidate centers of the clusters, if not, are just guesses to find them. And then based on those guesses, it calculates the Euclidean distance to all of the neighboring points from those clusters. And then it shifts the cluster centers slightly and recalculates the Euclidean distances, and then shifts the value slightly again. And it keeps doing this until the total distance that it calculates becomes a minimum. So it's got a procedure to automatically identify these clusters based on minimizing the distance from the center of the cluster and all the points in the cluster. It's very quick though. It sounds like some kind of a task, but it goes quite quick. The name of the function is k-means for k-means clustering, and all we have to do is provide it with the data set we wanted to search through. So I'm going to give it the trimmed Hawks data set. And I want to focus only on 2 columns of data, the tail versus the weight, but I want to go through all the rows we have. So all of the different species of the birds. So I'm going to put in a blank space and then a comma, so we have all of the rows indexed. And then I'm going to index by 2 column names. So I use the concatenate function in the location for the column, parentheses. And now I'm just typing the names of those columns, tail, comma, weight. Close square brackets. And then we'll say that there are 2 clusters to look for. Sorry, centers. The parameter is centers equals 2, which corresponds to looking for those clusters, 2 different groups. Press Command Return. And what we get as the output from there is a variety of information. We're told these are the coordinates that it calculated for the centers of the clusters. We have something called a clustering vector, which we're going to take advantage of in just a moment. It identifies, it tells you which cluster a given row of the data frame sits in. So we're going to use that to color the clusters in just a moment. And then Regression squares by cluster. And then here, this is a metric from topology regarding, I think it's a ratio of how many points are shared in the clusters versus the total points in the clusters. I'm not actually sure about that metric, but it's fine. Okay. So how could we use this to enhance visualizing our data? We assign the output of this test to a variable name. I'll call it cluster. So cluster equals, copy and paste the function call to the k-means test and run that line of code. So now this cluster object exists and I can access information from it. Now I'm going to define a new variable and add it to our hawks.trim table. It's going to be a new column that tells us which row in the data frame which cluster that row corresponds to. So I'm going to type hawks.trim $, cluster, and the assignment variable. So what we're doing here is we're adding another column to our data frame, a new column. And this is going to be this column of information for these cluster IDs. The 1s and 2s are for the 2 different clusters that R has identified, which means it's a factor object, or it needs to be a factor object. You have these repeating values of 1s and 2s. So this column, I want to make sure it gets read into the data frame as a factor. So I use the factor function. And then inside here, I type the name that I use to assign the k-means output to, which is cluster. This might have been a poor choice for the name. And then the object from that, here, $ for tab completion. The column, or the object from the k-means output that I want to use is also called cluster. I apologize, we've got the word cluster floating around a lot here. Okay, so we've now added that column to our data frame. We could view the data frame and see on the right end that it's been added, and it's a column of 1s and 2s. Like I mentioned, they correspond to the different clusters that these rows were ID'd to be sitting in. And we're going to use that to color the points, so we can visually see how they fit in different clusters. So finally, we'll call the Ggplot to make a graph of the data. So Ggplot data equals hawks.trim. Aesthetics, horizontal axis is weight, vertical axis is tail, +, we're graphing geom points. And for the aesthetics, I'm going to set color equal to cluster. It's a part of the same data set as the column name. Let's highlight these 2 lines and see what we get. Press Command or Control Return. And there we go. This is our tail versus weight data again from before with the 2 different species, but we're not coloring by species anymore. Now we're coloring by the output from the k-means test, the cluster IDs. And so this test was able to differentiate more or less the two species groups, and then color these points. So roughly, you can see where this boundary sits. This is where these points were identified to be just closer to the center of what would be the blue cluster versus the center of what would be the red cluster. But if you're looking at your data and thinking, well, I think that there's more than just these two clusters there, maybe this algorithm could also identify some more, then we can go back to the beginning and replace the centers equals 2 with centers equals 4 and rerun each of these lines of code. Regenerate the graph. Why didn't that work? Oh, I know why.
Change the second line there.
Oh, thank you. Perfect. Yeah. No, that's great. I totally missed the important one. Thank you. Okay. Now try again. Great. Now we have 4 clusters. Oh, this is, I think we still have all 3 species actually. So I think this is the species that only had 4 data points, and there's a couple of outliers from the other groups. And then it looks like both male and female hawks from this 3rd species were identified as one group, but then down here we've actually split by the male and female birds from the final group. So it's a great method for sort of exploring your data. You can use it also for doing, in some fashion, a statistical analysis of your data. I just wanted to introduce that real quick. Okay, so we have 20 minutes. We don't have enough time to go through PCAs. I apologize if you were really excited for that one. But I did try and provide a fair bit of information there for the data set that it's looking at, and some nice examples of visualizing results from PCAs. So I would encourage you to look at the non-blank R script that goes through those. So I'm going to skip PCAs. Sorry, are there any questions on clustering before I really skip PCAs? Yes.
Is there like a way to get it to like automatically decide the number of clusters for you?
No. At some point, the human has to make a decision, and then the machine takes over. And for this test, it's the number of clusters. Fortunately, it runs pretty quick, so you could just sit there and just kind of iterate. You could make a loop through numbers 1 to 500 and see how many. Well, you probably shouldn't do more clusters than data points. Sorry, my humor is getting the better of me. Okay, this brings us to our last part and then our final breakout session. We started this class by learning how to read data frames into R, so I'm going to end it with teaching you how to write them out of R and into a file. Nice closure. So suppose you want to save a copy of, oh, we didn't get the cars data because we didn't do that. Let's just call it hawks.trim. We want to save our trimmed hawks data frame to a file called hawks_trim. Save a copy of the changes. Hawks.trim data. Okay. It's going to be really anticlimactic. It's not the save function, it's called the write function because the practice is reading and writing data. So I'm going to type write, and automatically you'll see there's all kinds of automatically generated options. If I wanted to write table, 2 different kinds of CSVs, and there's even just a plain old write function for writing to other kinds of files like text files. And so there we go. So we'll use write.csv because we're going to write this to a CSV file. First, I tell our x equals which object from R I'm going to write to file. That's the hawks.trim data frame, sorry. Next, I tell it the name of the file that I want it to make. So I'll call it just hawks_trimmed or trim.csv. So automatically this is going to go to a working directory. If you wanted to send this somewhere else, then you could also include a path name in this instance for the file. And then finally, we have other parameters. Append. So maybe this file already exists and you don't want to overwrite the file, you want to just add on to the bottom of it. Then use the append equals true statement so that you just add content to the end of the file that exists as opposed to writing over it. Let's see, we don't need to talk about sep NAs. We can do the cars data look different. I'm not going to do the row name example. We'll just leave there and look at the output we get. So press command return for this write.csv output. And we go to look at, so in my folder, day 3 is my working directory, and I have now a hawks.trim CSV file that was generated just now. I can open it. And we have our columns and data that we had that we're working with from the Hawks data. Okay, any questions from folks on writing data to a file? Cool. Okay, the remaining 15 minutes, I have a few suggested exercises to practice the topics we learned from today. This says use the iris data as a suggestion, so you work with different data sets, and it's encouraging you to try making violin plots, color by species, and some XY scatter plots with added fitted lines to them. While you're doing that, as I mentioned, I'm going to pass back the, what's it called? Informed consent forms that you folks signed on day 1, and then I'll hand you the post-course, post-workshop surveys that are a part of that as well. Again, it's all voluntary, so if you filled out a pre-survey, it would be great if you could fill out a post-survey and use the same unique code that you did in the first case. And then we're done. Congratulations on a successful completion of your R workshop. So in the roll sheet, you had sent that around. Cool, that's great. Has anyone not been able to sign into the roll sheet? Daniel. Jessica. Jessica, so let's go. Osley. Osley. Ariel.
Here.
Ignacio.
Yep.
John Yi, I think. John Yi Yao. Oh, perfect. Anastasia. Enrique. Leonardo. Marcelo. Uraldi. Uraldi Lara. Thomas. Paula. Anna Montero. Carrie. Nick. Nick Santa Barbara. Augustina. Matthew. Nina. Yeah, Stephanie. Lee, Sean. Me. Jan. Oh, she's not. And then back to start. So again, Jessica, Celestica, Anastasia, Enrique, Giraldi, and Nick. Okay. So let's look at the family. Yeah, so it's not, it doesn't have .csv. Here it's not yes, and yeah, .csv. There we go. Yeah, it's already suggesting use Excel. That's just I'm not sure. That looks like it's something from the library. Can you scroll up somewhere? Right, yeah, so that's another package data table. Function package, function. Yeah, it's writing the object together. Well, so this maybe needs also to have .csv in the name. I'm not sure. Did that not produce what you wanted it to produce? Oh. Yeah, so I'm guessing it's probably because you need to add .csv in the name. Thanks. We recorded, yeah, we recorded those. Yes, the videos will be posted, I think, next week. And then, but all the materials are available email, so if you have emails, you should receive those.
Yeah, we can do that. Yeah, that makes sense. Just say, hey, the videos are up. Yeah, but. There was one that was. I think it's. Sure.
Yeah, effect size.
Yeah, here's this.
Oh, great. Thank you very much. Actually, this is for your records.
Oh, okay. I had another question. I don't think, because I'm interested in other workshops, so I don't think I'm going to be able to attend them this quarter. Like, do you
Like
ever
scheduling wise.
Yeah. Do you ever like upload these files for like other workshops?
Still working. I think it's still going around. It's somewhere on the. Oh, I think yeah. It's sitting on the counter
Does
there.
anyone not fill out the attendance?
Yeah, there's still whole front half. Let's see how many things I can multitask with at the same time. We usually do post these online with the course. So this is the first time I've taught this workshop in the laboratory, so these materials haven't been posted yet.
Yeah.
So there's slides, quote unquote, from the last one, but they didn't have much code in there, just sort of, topical slides like this what we're talking about, not really getting into it. But so these will probably be posted soon, a month or 3.
And so for like maybe isn't the next one like RNA-seq or something like that? Or like Python or something?
Sounds right. The intro to Python was last week.
Oh, okay. So if I waited, for example, if I find those files like these, like descriptions and then like code
for this
and stuff.
Yeah, eventually. I mean, I've also emailed this one out every day.
Oh, okay.
So, there. R will happen again next quarter. Right. So you include, yeah. So that is I have that. Okay. Yeah, and if I mean, if you use the same code. Thank you. Thank you. Next quarter. There are so the sequencing workshops, RNA-seq workshops use R. And so if you do your research, you sequence R. So there might be you might be should take Good question. Right. Let me come around. So perfect. Yeah. And anyone else still need the sign in row? Yes. Oh, that's okay. Yeah. You don't need to. It's only, yeah, so for us to use the data, we have to have both first and second. Roster that you attended. Yeah, no, we check. That's worth the survey. Yeah, because I'm collecting data from humans, so I have to. Thank you, human. By the way, you can keep
Oh, thank you. Sorry. Thank you. Well, we adjusted, sure. So, yeah, so like, I think that we're being short, right now, this is your regression until we're doing data for all the groups. But it's not controlling for groups. Actually, it's good. So, now when you say control, you can do one of the groups. Explain one of them much easier than the other one. One of them is we can do a regression for each of the groups individually. So that would just be factories where you index the data. So we go into Excel files and we use index techniques to grab only the subset. Subset for male shirts or male. Then once you subset, you do the regression on just that subset. Yeah. Another way is can be automated R with oh yeah, try that. Time sense. So again, it's different between design just. So what this did, so you have this data, and then you have this cluster, and you have this cluster. So it fit one line through all the data, and then it said just show the different sets of groups. All we have to do is add it's just a vertical offsets for these different groups. So if you wanted actually for this bottom group, then you just have to subtract by some amount. The top group can add by some amount. But it doesn't change the slope. So it just changes the data points. Yeah. It shifts vertically up and down, change the y-intercept so that it runs through different groups. It's not changing the slope that we get. So that's why I'm saying it depends on the and adjust or control variables. Yeah, the reason why is because just guesses explanation. You can tell the first number that's useful. And I would subset just the regression of this subset. So that you allow for the slope to change. Because this other scenario where you regression the whole data set, but then you got these additions for if I wanted to vertically offset and focus on the other group,
zeros. The fact that the slope is fixed doesn't mean that you still have a stable slope. So I think that means you want to subset.
And so when you subset, you individually run it.
Yeah, you could have a slope here.
Right. And then at that point, that's not. It's really the results will flash.
Yeah, so it would be like.
When you're subsetting this information as zero as it is, that's why I'm saying I don't think that's exactly what I think that's how you progress the whole thing. Because you have, as you did, use that information.
It's gonna be the same. We'll go on.
Plan on sex.
It'll be fine.
Oh, I forgot to point out that I have
Direction
shared. No, this is good. Scroll down here. I listed some references online that are very this one, STHBA. So this is a nice collection of visualizations. As a website as a whole, it's a great website. It's a lot of, I remember finding some examples of doing
There will be a time.
regression plot.
Yeah.
But I wouldn't.
It's just, it's very, like,
Yeah, that's a big. Yeah, I'm pretty sure what you want to be doing is very possible.
yeah.
It's just the problem is I don't normally do that, so I'm not sure which examples I actually want. It sounds like you want. Yeah. Oh, maybe.
Maybe, I don't know.
That's what I was saying. You could just do both and show your advisor. Say, here's the graph with the lines and subset it with the groups. Here's the graph with the lines that you don't. Let's see if which one is.
But do we, this, it's, it only changes, the position.
Correct.
That's,
Yeah, it's on, but the idea is that it's supposed to apply to predicts for it's like, oh, I have this curve for the female instructions, and if I want to predict for male instructions, I just take weight and then add an extra value to it. If it's
This is one where you can. When it comes to your colors, well, actually, one time I tried to show them.
I appreciate it.
thank you. That kind of makes sense, helps a lot.
Great. Yeah, that's normal.
Yeah.
It'll come.
I feel like that was my parents.
Sure.
There's some methodology tracking that just clusters like
How does it do? So when you say find 4 clusters, it's okay, we'll look for 4. And then it makes these guesses as to where these cluster centers might be. You can, the centers, like a coordinate point. No, not a mean, a location in the tail weight space. So here's a location here. I mean, I guess you could think of it as a mean of these values in some way, but it's not how it's calculated. So it finds, it just guesses a point, maybe it gets this point over here, and does the same for the other sections. And then it calculates from this point, it calculates the distance to all of the neighboring points.
The neighboring point, for example, the point that should be here is the neighboring point is red point.
Mhm. Yeah.
All right.
Yeah. And then it moves the cluster, or it moves that test point a little bit to see if, when we move it and then recalculate, does the distance to all the points get bigger or smaller when we move? And if it gets smaller, that means we're still finding the minimum, or sorry, the center of the cluster. And so it uses that algorithm, that sort of iterative process, to find the center location for the cluster.
So it doesn't actually.
It does very automatic. Yep.
You just want to.
Yep. And then it'll run it for you.
Thank you.
Yep. You're welcome.
Do you have any after videos, for example, videos of the session?
We're going to host them. For me, I have to stop recording.